Hello all, welcome to this video on Networking Lab. Today I'll be talking about link state routing protocol, its implementation in C and comparison with distance vector routing protocol. Link state protocols are also called shortest path first protocols. They have a complete picture of the network topology. Hence they know more about the whole network than any distance vector protocol. Examples of link state routing protocols include OSPF, which is Open Shortest Path First, and ISIS, which is Intermediate System to Intermediate System. There are also routing protocols that are considered to be hybrid in the sense that they use aspects of both distance vector and link state protocols. EIGRP, which is Enhanced Interior Gateway Routing Protocol, is one of those. It is a dynamic routing protocol used for routers' decisions and configuration. They only send incremental updates, which in short reduce the workload of the routers and the amount of information transmitted. Now looking into the working. Whenever a new router is initialized inside the domain of an autonomous system, the first thing it determines is the cost of the links on each of its interfaces. Once it is done, the router advertises this information to all the routers present in the domain, and it keeps monitoring the cost of the links onwards. If the router observes any change in the cost of the link at any of its interfaces, then the router again advertises this change to all the routers in the domain. Now in this protocol, each router has information about the set of link costs of all the routers in the domain. So each router develops the topology of the entire domain. It can now calculate the shortest path and build a routing table using the Dijkstra's algorithm. Link state routing protocol cannot be used as an exterior routing protocol or inter-domain routing protocol. The first reason being, in a large network like the internet, different autonomous systems may use different link metrics. As the metrics vary from one network to another, this prevents the link state routing to be used as a consistent routing protocol. The second reason is that link state routing involves the flooding of link state information to all the routers in the domain. If we use it as an inter-domain routing protocol, the flooding across multiple autonomous systems may be unmanageable. Now looking into the steps for link state routing. When a router is initiated, it identifies its neighbors and their network address. It sets the cost metrics of the link at each of its interfaces connecting to its neighbor. Then it advertises the link state packet containing the link state information to all the other routers in the domain. It also receives information from other routers. Then it calculates the shortest path to every other router in the domain and prepare a routing table. Now, the building of routing table. When building a routing table, the routers have to ensure that they are showing the shortest path to every other router in the domain. Building of routing table involves the following steps. The first being, the router has to create a link state packet which contains a set of link costs at each interface of the router. Then it distributes this link state packets to all the other routers in the domain, not just the neighboring ones. Then they form the shortest path tree for each router, and finally the routing table with the shortest path to other routers in the domain. Now let us look into each of these points in detail. The first one is formation of link state packet. The link state packet has information about the router in detail. It has information about the router's identity, list of links, sequence number, and age. This helps another router in the autonomous system to understand and make a topology of the entire domain. The sequence number helps in receiving routers to compare between the old link state packet and the new link state packet, and also facilitate flooding feature of link state routing. The age of link state packet helps routers in the domain to decide the time at which they must be discarded. They are created by routers in the domain at two events. The first is, whenever there is a little change in the topology of the domain, The link state packets are disseminated, informing all the routers in the domain, updating them about the change. Dissemination of the link state packets at a periodic interval ensures that any router in the domain does not contain the old information. The timer set for this is around 60 minutes to 2 hours. The long interval prevents the flooding features from creating too much traffic in the domain. The second step was flooding of link state packets. The transmission of link state packets to all the routers in the domain is referred to as flooding. The routers receiving the link state packets first compare it with the LSP it has already received. If the new link state packet is older than the previous link state packet, the newly received is discarded, else the router disseminates a copy of the link state packet through all its interface other than the one through which it had received it. The third step is creation of the shortest path tree. As each router has information about each other in the domain, each one of them creates the topology of the entire domain. To determine the shortest path to every other router, the shortest path tree must be created. It has one root node, that is the router for which the shortest path tree is created, and several other nodes, that is the rest of the routers in the domain, called leaf nodes. It expresses a single and the shortest path to every other node in the tree. And the final step is creation of routing table. Using the shortest path tree, each router creates a routing table which has 3 columns, namely destination, cost, and next router. Now looking into the advantages of this protocol. Link state routing protocols create a topological map or shortest path first tree of the network topology. When receiving a link state packet, link state routing protocols immediately flood them out all interfaces except for the interface from which it was received. This way it will achieve faster convergence. After the initial flooding of link state packets, it only sends out the link state packet when there is a change in the topology. The link state packet contains only the information regarding the affected link. Also, link state routing protocols do not send periodic updates. Even though this technique works efficiently, problems can arise. Usually problems occur because of the changes in the network topology, that is the links may go up or down, and all routers do not get updated immediately because they might not be having the same line speeds. Therefore, routers connected via a fast link can receive these changes faster than the others on a slower link. Different techniques have been developed to deal with these problems, and they are dampening of update frequency, exchanging route summaries at area borders, and managing partitions using an area hierarchy. Now let us see what greedy algorithm is. A greedy algorithm is an approach for solving a problem by selecting the best option available at the moment. It doesn't worry whether the current best result will bring the overall optimal result. The algorithm never reverses the earlier decision, even if the choice is wrong. It works on a top-down approach. This algorithm may not produce the best result for all the problem. It's because it always goes for the local best choice to produce the global best result. Now, Dijkstra's algorithm is a type of greedy algorithm. It is used for finding the shortest path from a source node to all other nodes in the graph. So it gives you a single source shortest path. It only works on weighted graphs with positive weights. Its time complexity is big of E log V, where E is the edge and V are the vertices. Its space complexity is big of V. Dijkstra's algorithm require a graph and a source vertex to work. The algorithm finds locally optimal choice, that is local minima in this case, at each step of the algorithm. Each vertex will have 2 properties defined for it, the first being the visited property. This property represents whether the vertex has been visited or not. We are using this property so that we don't revisit a vertex. A vertex is marked visited only if the shortest path to it has been found. The second property is path property. This property stores the value of the current minimum path to the vertex. The current minimum path means the shortest way in which we have reached this vertex till now. This property is updated whenever any neighbor of the vertex is visited. The path property is important as it will store the final answer for each vertex. Now let us look into some of the applications of Dijkstra's algorithm. It is used in social networking applications, in telephone networks, and to find locations on the map. Now let us see an example for Dijkstra's algorithm. This is the graph that is given. You can see all the weights are positive. Now this is the table. Now this problem will be done based on the program we have written later. So in that, initially all the distances will be maximum, that is infinity. So in C, we can assign int max instead of infinity. That is the highest maximum value possible in the compiler. And the distance from source to source is 0. That is why the first node has 0 as its distance. Now when we start with from the source, we can mark it as visited. And since that is the only distance known, we can mark it as 0. Now I have marked 0 as visited so that I need not consider this distance again, because that is the minimum distance you can get. Now on examining 0, I see that there are two connections, 1 to 1 and 1 to 2. And there are distances 10 and 3. But the distances here are infinity. So I can update the table with these values 10 and 3. Now looking into 3 and 4, they are not reachable from 0. So we can say that they are at infinity. Then what I do is I look into the minimum value in this particular row. I see that the value 3 is minimum. So I'll mark 3 as the minimum distance, and 3 is the distance at node 2. That is the minimum distance. So I will mark 2 as visited and write this value 3 here. So we have 0, 3. And similarly for 1 also I have got the distance as 10. So I'll write it here as 10. Now next what I do is I'll take the outgoing edges from 2. That is to 1, 3 and 4. They have distances 4, 8 and 2. Now I'll update those values in the table. The edge to the node 1 has the distance 4. Now looking at from the source, it will be 3 plus 4, which is 7. Next I'll look into the edge to 3, which is of distance 8. Now looking from the source, it will be 3 plus 8, which is 11. So which is less than the infinity. So I can update it. We have considered this 7 here because the existing distance is 10. So the value 7 is lesser than 10. So we could change it. Then looking into the edge to the node 4, we see that the distance will be 3 plus 2, which is 5. That is updated here, which is less than infinity. Then I'll take the minimum distance from this row, which is 5. I'll mark it and take the corresponding node 4 as visited. Then from 4, we look what are the outgoing edges. We see that there is only one, that is to 3. And if we take it into consideration, we see that the distance from source will be 5 plus 9, which is 14. We have already the distance 11, which is lesser. So we need not update it. And 7 is carried forward similarly because there is no other edge from 4. Now I'll take the minimum from these two, which is 7. I'll mark it and I'll mark the corresponding node as visited and give this 7 there. So all these values marked in blue are marked against the node here also, 0, 7, 11, 3 and 5. Next what I do is I look into the outgoing edges from the node 1, which is to 3 and 2. Now looking into this, that is to node 2, it will be 7 plus 1, 8. We need not consider it here because 2 is already visited. Now looking into this edge to 3, it will be 7 plus 2, which is 9. Existing value is 11. Since 9 is lesser, we can write it here. And since that is the only value in that particular row, it will be marked and the corresponding node will be marked as visited. So the final distances from the source will be 0, 7, 3, 9 and 5 for each of the nodes 0, 1, 2, 3, 4. Now in the previous video on Bellman-Ford algorithm, I had skipped on giving an example of how that particular program is done. Now this is the graph that I have considered in the previous video for demonstrating how the program worked. We can see that we have negative weights in case of Bellman-Ford algorithm. As in Dijkstra's algorithm, we will take all the distances as infinity in the beginning and the distance from source to source will be 0, which is marked here. And next what we do is we'll take the two edges from the source, which is to these two. We see that the distance is 2 and 4, which will be marked inside here, and the same will be updated here. And since they are lesser than infinity, we can take them into consideration. Similarly, for the next case, what we do is we are going for the outgoing edges from these two nodes, which is to this and this. So taking this distance will be 2 plus 2, that is 4, and this will be 4 plus 3, which is 7. Now we can see that all the nodes have been covered. So for the next iteration, what we can do is we'll check if there is a distance which is lesser than the values obtained here. So when we look into that, we'll see that in order to reach here, there is a better path than this, which is through these edges, which is 4 plus 3, 7, minus 5, which will be 2. So this 4 will be replaced by 2 because we have got a lesser value. And we'll run again for a final iteration. Since there are 5 nodes here, we'll go for 5 iterations. On the 5th iteration, we'll see that there are no changes to be made. So it will have the same value as the previous one. Now this is how we find the shortest path for Bellman-Ford algorithm. Now let us look into a comparison between distance vector routing and linked state routing. Distance vector routing uses Bellman-Ford algorithm, whereas linked state uses Dijkstra's algorithm. Now for distance vector, the convergence time is moderate. That is good news forward fastly as compared to bad news. Whereas in case of linked state, the convergence time is fast. For distance vector, there is less utilization of CPU and memory, whereas in linked state, there is more utilization of both. In distance vector, there is a problem of persistent looping, whereas in linked state, only transient looping occurs. In distance vector, the best path is determined by the least number of hops, whereas in linked state, it is determined by the least cost. Distance vector doesn't have a hierarchical structure, whereas linked state has one. Distance vector requires smaller bandwidth as there is no flooding. The packets are small and the sharing is local. Whereas in linked state, they require larger bandwidth for flooding problems and for transmitting large linked state packets. In distance vector, it updates table with information about its neighbors. So it works based on local information. Whereas in linked state, it has the information of the whole network. Therefore, it works based on global information. Distance vector updates based on broadcast, whereas link state updates based on multicast. Now we look into the logic of the program that we have used here. This is the code where we are setting the distances initially to infinity, which is by int max, and we have a separate array in case of link state to know if the node is visited or not. Initially all the nodes are unvisited, so the values will be 0. After the loop, we'll mark the distance from source to source as 0. Now the next step is to find the link with minimum distance. So what we do here is h is the number of hops. We'll run a loop with h as the limit. Then we'll check whether the particular node is visited or not. If it is not visited and if it has a distance that is lesser than the existing minimum value, what we do is we'll note this new distance as the new minimum, and we'll also note this index and mark it as the minimum index. Now this is done till all the hops have been covered. And finally what we do is, since we have visited this minimum index node, we'll mark its visited value as 1. Now this is the portion where the distance update is done. Now for the distance to be updated, we need to satisfy some conditions. Not of visited means the node should be visited. The visited value should be such that it has already been covered. And if the node is visited, and we are checking the adjacency matrix. Now this is the input that is given to this program that will give the distance between all the nodes in the graph. So we are taking the adjacency matrix value for the minimum index and this node into consideration. So we are checking if there is an edge between these two nodes, and we also see if this node has a distance which is not infinity, and also if the distance of this node added with the adjacency matrix value will give us a better distance. That is, if it gives a lesser distance than the existing distance, then we'll surely need to make the updation. Now for this updation to happen, please note that all these conditions need to be satisfied. Now this is how the program looks. Limits.h is added since we are using the int max macro. Now here the number of hops is entered, then the adjacency matrix is read into. Then this is the portion where the distances are initialized, setting it to infinity and the visited array to be 0 and the distance from source to source being 0. And this is for checking the minimum distance. So here there is a main loop with a variable called round. It traverses through each hop and checks for the minimum distance. Then what it does is, it will also run the checking where we need to see if the distance has to be updated or not. Now this is repeated until all the hops are covered. Finally, we will display the source, the name of the hop and the distance from the source. Now this is how a sample output will look like. Number of hops, adjacency matrix, the vertex name and its distance from the source. Note that here in this example 0 is the source vertex. Now let us look into this example. It's a demo of the program we have already seen. This is the program. Now taking the terminal, I'll compile the program gcc lsr.c. After successful compilation, the program is run. ./a.out. They've asked for the number of hopes, which is 5 in this case, and the entry for the adjacency matrix is given, since the graph itself is not read into here. If there is no edge between two nodes, the value will be 0, else it will be a positive value. The number of entries, that is the number of rows and the number of columns, will be equal to the number of hopes here. That is, we'll get a 5 by 5 matrix. And this is the final output that we get. That's all for now. Thank you for watching.